This is the, I guess, eighth pin cast in a series on first order circuits, the solution to first order circuits. And in this pin cast, we're going to look at analyzing circuits that are driven or forced or powered by voltage or current sources which are piecewise constant. Okay, and let me describe what I mean by that. So we would have maybe a voltage source like this. We'll call it Vs of t, and perhaps we would have a voltage Vs of t that would start from 0 volts, and then at some point it goes up to, let's say, 2 volts. Okay. Perhaps later it ends up stepping down to 1 volt. Okay, so at 0 times 0 it goes to 2 volts, and then maybe at 1 second it goes down to 1 volt, and it could keep switching around. But the point is that within any interval of time it is constant, but then it can switch to another constant value. And we're going to look at how we can analyze the first order response of a system that is driven or powered by such a source. Now I want to introduce a useful construct to help us to efficiently represent these type of sources. So I want to define what is called the unit step function. In physics, it is called the Heaviside function. Okay, in physics. And it's a simple function. Sometimes it's referred to as u of t, sometimes c of t, and sometimes, in the way I will refer to it, is I will actually use the strange notation of 1 of t. Okay, and these will all be names that we might use for the unit function, unit step, but I'm going to use this this notation here. And here's the definition. It is 0 for time less than 0, and it is 1 for time greater than 0, and it's actually undefined at time exactly 0. It's transitioning between 0 and 1. So it's just a step. Here's time, and it steps from 0 to 1 at time 0. Okay? That's the function. Now what's really useful is that we can use this unit step function to describe piecewise constant signals, just like the Vs here that I show over here. So before I do that, let me bring up a slightly different function here. Let's say it is a unit step, but when it steps to 1, it actually steps at the time 2 seconds. Okay, how would we describe that function? Could we use the unit step to describe that? The answer is yes. We can say it is equal to 1 of t, and then it's going to be shifted. It's delayed by 2 seconds. So this is 1 of t minus 2. Okay, so we could put both of these together. If we said consider some function f of t equal to 1 of t plus 1 of t minus 2, then what we would have is a function that starts out at 0, it goes to 1 at time 1, and then at time 2 it's going to jump up to 2. Okay? This is 1 and this is 2. So now let's think about how we could construct this signal here. We could construct this as Vs of t is equal to, well, we see a step at time 0, but it steps by 2. So we'll say 2 times 1 of t, okay, and that would give us the the step at time 0 going up to 2, but it just keeps going, right? At 1 second, though, we need to reduce that by 1 volt. So we'll put a minus 1 times the unit step, but it's not going to be at unit step at time t. It'll be 1 of t minus 1 second. Okay, so this one here is basically a negative step, minus 1, and that occurs at 1 second. And you add these two together. Okay, so you can see how using the unit step definition allows us to describe describe a piecewise constant function. So let's consider a pulse. What if we had something that started from 0, at time 0 it goes up to 1, and then it goes back down to 0 at time capital T. Okay, we could describe this as being equal to the unit step at time centered at time 0 minus the unit step delayed by capital T. Okay, so now we've looked at some circuits that have involved some switches, right? So we had one circuit that involved a switch that simply opened at time 0. And we have to be careful with this kind of circuit here. I'll tell you what we have to be careful about after I show you two different scenarios here. So let's call this VG, okay, just some voltage here. This actually comprises two different circuits. When time is less than 0, what we have is just the voltage source. Okay, VG. That's when t is less than 0. But when t is greater than 0, the switch is open. And so we have basically an open circuit, if you will. Okay? And what we can replace that with is we can leave it open, or we could also put it in as a current source and say it's 0 amps. Okay? And the reason I do that is to highlight that sometimes when you have a switch circuit like this, where there's a switch, a path in your circuit that's literally opening up or closing from being open, you're actually changing the topology. It's like you had a battery there and you took it out and replaced it with a current source, albeit in this case a 0 amp current source. So this kind of circuit we cannot represent using this idea of a unit step function, because we're not simply talking about this voltage source or the voltage across this terminal pair here going from one forced voltage VG to another forced voltage. Okay, but let me show you an example where you could use our unit step to help us out. So here's another circuit. We'll say this is VG, and it's grounded here. And now we have this scenario. So now what we have is this is a single pole double throw switch. So in other words, for time less than 0, the switch is in its upper position and it's connecting VG to this terminal pair out here, this output. At time 0, it switches from being in the up position to being in the down position. Now it connects it to ground. Okay, so we have two circuits here. The first case is VG connected to the terminals. This is for t less than 0. In the second case, we still have, if you will, a voltage source, but it's a 0 voltage source, right? Because it's a short. This is for t greater than 0. This can be represented by a voltage source that uses the unit step. So in this case, let's see, we have a voltage of 1, or a voltage of VG, I should say, minus, then at time, minus a unit step. Okay? That's what this is equal to. All right, so the first part here is just constant at VG. The second piece here scaled by Vg is going to be something that steps down to minus Vg at time 0. Okay, so we can use the unit step to represent a switch with a voltage source, provided that it's a switch that's a single pole double throw. Notice that in both cases there's a path for current to flow here, right? Whereas in this first case, when you open that switch, there's no more current path. So you've actually replaced the voltage source with a 0 amp current source. So I just wanted to point that out so you would maybe see some connection with the examples that we worked before where there was a switch that was opened, and say that in that case you cannot replace it with this unit step or some weighted sum of unit steps, but with a single pole double throw switch where you're going from one voltage source to another voltage source or from one voltage source to ground, you can. So to maybe reinforce this one last time, let's think about this scenario here. What if we had a 10 volt battery, okay, and then we had a 2 volt battery, and we have a switch, and the switch gets thrown from the up position to the down position at time equals 0. Okay. So with this, how we'd represent this is we could have a 10 volts times times the unit step, and then minus. We're going to drop from 10 volts to 2 volts once the switch is thrown. So we'd say minus 8, right? That's the difference between 10 and 2. Minus 8 times the unit step delayed. I'm sorry. No, this doesn't have a unit step. This is just 10. Okay. And then minus 8 unit step centered at time equals 0. So we could model that switch and voltage source configuration using our unit step function. Okay, so now what we want to do is we want to consider a circuit, a simple RC circuit. Okay, so we're going to pick the simplest possible circuit that is first order, but we're going to now have a Vg of t, this voltage source here. We have an R, we have a C, we have a Vc, and we're going to define Vg as this pulse. Let's say it has an amplitude of 2 volts, and it goes from 0 seconds to 1 second. And we want to find the response. Find Vc of t, okay, for all time, and assume that Vc at time 0 is equal to 0. So before we go analyze this, let's just see if we can anticipate what this response might be. I'm going to break this signal up into the two well, first let's write it as the sum of unit steps. So we'd have we could write 2 volts, or we could do it this way. We could write 2 times 1 of t, right? 2 times 1 of t minus 2 times 1 of t minus 1 second. Right? So in the first case we've got a step that goes to 2 at time 0. In the second case we have a step that goes to negative 2 but occurs at 1 second. Okay. Now this circuit is linear, so we can actually use superposition. We could actually redraw this circuit as really being the sum of 2 voltage sources, if you will. Okay, where one is a 2 times unit step, and the other one is minus 2 times unit step delayed by 1 second. You could do that, and then we could use superposition. That's one way of solving this. Before going further with that, let's just think about if we can get an intuitive sense of how this circuit will respond. We know that if you apply a unit step or 2 volts to the circuit, to Vg, 2 volts is applied to the RC elements, series pair, and the capacitor starts at 0, you're going to get a capacitor voltage that's going to charge, right? It's going to rise, so it'll end up looking like this. This would be Vc. Now if the input VG stays at 2 volts, this will actually eventually asymptotically reach 2 volts. Okay. However, we also know that if there is some voltage on a capacitor and you connect a resistor across that capacitor, and there's just the capacitor and the capacitor will discharge down towards 0 from its current state. And so, and that is precisely what happens beginning at 1 second. At 1 second, the source goes to 0 volts, and we have no source that's really driving the circuit anymore. We have a resistor and a capacitor in series, and the capacitor is going to discharge. So if this happens to be 1 second here, then at this point here, we're going to see the voltage discharge again. Okay, so this is the response that we expect. I'll color this in just so you can see which part I'm talking about. This is what we're talking about. So that's what we expect. So now how do we go about solving it? Well, we're going to, we can separate it, we can solve it 2 ways. One is we can use superposition, and 2, we can solve it for time t from 0 up to 1 second, and then solve it as a separate solution from time 1 second on. Okay, so we'll try both of these. So let's first solve for t equal to 0 to 1 second, and then here we're going to solve for t greater than 1 second. Okay, so when in the time period of t 0 to 1 second, the circuit we have is we have 2 volts driving our RC. And we can write the response here by inspection at this point because we've solved this enough. It's going to be VC is equal to, the final value will be 2 volts, right, 2 volts. And the initial value we said was 0. So it will be a 2 times 1 minus e to the minus t over tau. Okay, it'll just look like this. Okay, and we can also say then, well, okay, we'll stop there. And then for time greater than 1, the circuit that we have is just an RC. Okay, so VC of t then is going to be equal to the voltage at 1 second. Okay, that will be the initial condition for this circuit now. We have charged it for 1 second, and the capacitor voltage has reached some value. So this voltage here, at this point here, is VC of 1 second. So it'll be that voltage times e to the t over tau, except because this is happening at 1 second, we're going to say it's at t minus 1 over tau. Okay? So what we're saying is it starts at some voltage VC1 and decays down, but it's beginning at 1 second. Okay, and the value here is VC of 1, which is, we can just use our solution from the first interval here, which it's going to be 2 times 1 minus e to the minus 1 second over tau. So therefore we can write VC of t will be equal to 2, 1 minus e to the minus 1 over tau times e to the minus t minus 1 over tau. Okay, and now we can put this all together. Maybe I can fit it here. So the complete solution will be VC of t is equal to, and we'll have 3 cases. For time less than 0, the voltage is just going to be 0. For time between 0 and time 1 second, we will have 2 times 1 minus e to the minus t over tau. And for time greater than 1 second, we will have 2 times 1 minus e to the minus 1 over tau times e to the minus t minus 1 over tau. This is for time greater than 1. And this, if you plot this, will look just like what we have here. Okay, so as an example, you might ask, well, something that might be asked of you is, what is the peak voltage on the capacitor? So to do that, the peak voltage, let me just write here, the peak VC max, I guess, or peak, will be equal to VC at time at 1 second, okay, at the end of our pulse. So that'll just be equal to 2, 1 minus e to the minus 1 over tau. So we need to know tau, which is RC, before we can actually calculate that. Let's look at a little modified circuit example. Let's say that we had a voltage source, same circuit, VC, but now our VG of t, let's suppose that now it was going to go from 2 volts up to 4 volts. Okay, and this was going to happen at, so it'd go at 1 second, and then let's say it goes back down to 2 volts at 3 seconds. Okay, and now we want to find the solution again. We want to find VC of t. Find VC of t. Assume VC at time 0 is equal to 0. Okay. So the first thing we have to do is we have to find, we have, what is the circuit for time less than 1 second? Okay, the circuit we have there is we have a 2 volt battery connected to our RC. And so we have there that the voltage, since it's been there forever, right? So the idea is before, nothing is switching before time t equal 1. So it's been at 2 volts forever. So the circuit is in steady state, and the capacitor voltage is equal to, in this case, equal to just 2 volts. Okay. For time greater than 1 second, but less than 3, okay, the circuit that we have now is a 4 volt circuit, right? So here we have VC of t is going to be equal to, all right, the steady state value, if we stay in this circuit mode forever, is going to be 4 volts. So we'll have 4 volts plus, okay, and then we have the initial condition. What is the initial condition on this voltage, this capacitor? Well, right at 1 second, the capacitor has been basically sitting at 2 volts forever. So our initial condition will be 2. Okay, that's actually coming from here. Then minus 4, which is really just our steady state. This is our steady state value. And then we have e to the minus. We're going to do t. And because this step happens at 1, it'll be t minus 1 over tau. Let me rewrite that. It'll be 4 minus 2 e to the minus t minus 1 over tau. Okay, and then lastly, for t greater than 3 seconds, the circuit we have is back to 2 volts. Same as before. So now we have VC of t is going to have a new steady state value, right? It'll be 2 volts plus the final value from the final value of the value of the capacitor at time 3 seconds, right? So that'll be VC at 3 seconds minus 2, which is coming from here, times e to the minus t minus, now we're talking 3 seconds over tau. Okay, so let's rewrite this. So we have VC of t will be equal to 2 volts for t less than 1. Then it will be 4 minus 2 e to the minus t minus 1 over tau for time between 1 and 3 seconds. And finally it will be 2 plus Vc of 3. So Vc of 3 is actually 4 minus 2. E to the minus, and now we plug in 3. 3 minus 1 over tau. Okay? That minus 2 volts. E to the minus 3 minus t minus 3 over tau, excuse me, for time greater than 3. Okay, so let's plot this. So it starts out at 2 volts. And at 1 second, it will now start rising exponentially. Okay, and it would tend toward 4 volts. Okay, but it will never get there. All right, and before it gets there, we'll arrive at 3 volts, and now at 3 volts, we'll arrive at 3 seconds, and at 3 seconds, the source goes from 4 volts back down to 2. And this value right here, okay, that is this value here, okay, it is Vc at 3 seconds. So we'd have to compute that, have some values to plug in. But from here on, now this is going to decay back down, and it will approach 2. So if you look at this last equation here, as time goes toward infinity, this second term will vanish because it's an e to the minus t minus 3 over tau. So that'll vanish, and we're left with the 2 right here. So this will asymptotically go back to 2 volts. Okay. So what I wanted to show in this example is that we can also consider cases where the voltage that's driving the circuit is actually going between two non-zero values, not going from 0 to 2 volts or and back, but it could be going from, like in this case, 2 to 4 volts, and then back. And you can see how, in principle, you could have a number of steps, more of these, and you could continue to construct the response. The key thing to remember is that the final value just prior to the next step becomes the initial condition for the next solution in the following period interval of time.